Hey everyone, this is the second lecture of Astronomy Geoscience 160, Life in the Universe. I'm going to split this one class period that would have been normally a 50-minute class period into three smaller, shorter sections, and this is the first one of those. In this section, we'll be talking about atoms, elements, subatomic particles, and molecules, basically the things that make up the entire universe. So if you go outside and you look around, you notice that our world is complex. There's all sorts of different stuff. There's water, there's liquids, there's air, there's clouds, all of these beautiful trees and living things. And for millennia, scientists have been trying to find patterns in the building blocks of nature. One of the earliest ways that people tried to break down everything in the world around us is by dividing it into fundamental building blocks called elements. One of the first attempts at coming up with a set of elements to describe our universe was in the early times in the ancient Greeks, who thought that four fundamental elements were air, fire, water, and earth, and that these could describe basically everything around us, and that these were essentially fundamental, and that they were things that couldn't be divided or changed around any further from what they already are. But it turns out that on closer inspection, these proposed elements are not necessarily fundamental, because you can create some of them from the others. So in this GIF here, I'm showing what happens when you mix vinegar, a liquid, essentially water, with baking soda, which is a solid. And what you end up doing is you end up creating a gas or air. So you've now created one element from the combination of two others. Here's another example of this. Water, when you pass electricity through it, can be broken down into two different gases. So water plus electricity equals air. Yet another example of how these fundamental elements didn't end up being so fundamental after closer inspection. So over the centuries and over the millennia, scientists have settled on another set of fundamental elements. And here's a list of them here. There's more of them, but these behave in a way that's more like what the ancients had in mind when they started trying to figure out what everything was made of. If you group these elements together in a certain way, this known as the periodic table of elements, you find that many of the elements that are near each other on this periodic table have similar properties. So for example, this column over here of elements are highly reactive and explosive, and many of them will combust explosively if you just put them in water. Whereas the elements over here on the right-hand side are stable, unreactive gases. So these different elements seem to be grouped similarly. We see patterns that emerge. So this helps us understand that this probably is a pretty good fundamental way of expressing what our world is made of. So we've seen that the elements have specific properties and that elements that are grouped similarly together have similar properties. But what actually causes these properties? To understand this, you have to go down to the atomic scale. And by atomic, I mean the scale at which you no longer split an element and have it remain that element. So what do I mean by that? So take this gold bar, for example. I can take this gold bar and split it in two. And now I have two smaller pieces of gold. It's still gold. It still has all of the properties of gold. I can split it further, and I can split it a lot, many, many times further, and it still remains to be gold. But at some point, there is a smallest possible unit of gold, and we call this an atom. If we take this atom of gold and we split it, then the two parts that remain are no longer gold. So that's what we mean by the atomic scale. It's kind of like if I had a pair of handcuffs and I split these pair of handcuffs in two, then the two parts are no longer a pair of handcuffs and they don't function in the same way and they don't have the same properties anymore. So atoms are the smallest unit of the elements, but they can still be split. And they're actually made up of things that we call subatomic particles. Here are a few of the different subatomic particles that we'll encounter most often throughout our course. So one of them is called a proton, one of them is called an electron, and one of them is called a neutron. These subatomic particles are so small that we can never really see them. They don't even interact with light in the way that we expect normal objects to do so. but they do have certain properties that we can measure and that help us understand their behavior. One of the important properties of these particles is mass. So we all have a pretty good fundamental idea of what mass is. It's basically how much of something there is, how much heft that thing has. So it's not related to size necessarily, although the more size you have, the larger an object is, oftentimes the more mass we'll have. But for example, this marshmallow and this 2 kilogram weight are basically the same size, but this one has much more mass because it has much more heft. Think of mass as how hard it is to get something to move if you were to try to throw it. Another property, and it turns out that we can measure the masses for all three of these subatomic particles, and they're all very small. So the mass of a proton is 1 billionth of 1 billionth of 1 billionth of a kilogram. So that is unimaginably small to us. A neutron is about the same mass, and an electron is 2,000 times smaller than either a proton or a neutron in mass. So these are really, really tiny objects, but in the subatomic world, the protons and the neutrons are much more massive than the electron, and they can pull it around as a result. Another property of these particles is charge. We also have some familiarity with charge, especially in a cold winter day like today, where if you get out into the car and you try to get out of the car and you have a furry coat on, you might accumulate a charge and you might zap yourself when you touch the car door. This is a manifestation of this phenomenon that we call charge. So this is something that's a little bit familiar to us. We've all probably experienced when we get zapped by static electricity or when we rub ourselves with a balloon and it causes our hairs to stand up. And what's really going on here is that these processes cause us to gain some charge compared to our normal state. There are two flavors of charge. You can be positively charged or negatively charged. And it's not that one charge is better than the other. One of them is positive and one of them is negative. They're just opposites. That's all we mean by that. And the key idea here is that two similar charges repel each other. So if I have a positive charge here and a positive charge here, they will try to push each other apart. And you can see this when this woman takes her hat off. Once she takes her hat off, her hair is positively charged. And as a result, the two positive charges in the two different strands of hair repel each other, and that's why her hair stands up a little bit instead of falling back down like normal. On the other hand, opposite charges attract each other. So this fellow over here has managed to create an opposite charge. He has a negative charge in this balloon and a positive charge in his head. And that is why the hair is trying to reach up to the balloon. The negatively charged balloon is attracting the positively charged hair and causing it to pull upwards. So in the subatomic world, the proton is a positively charged particle. The electron is a negatively charged particle, and neutrons have no charge. And what you can take away from this is that the proton and the electron should attract each other, and in fact, they do. So atoms are made up of these subatomic particles. Typically, the protons and the neutrons all hang together and are tightly bound together in something called the nucleus. Because these are the heaviest particles, the most massive particles, this is where most of the heft of the atom is. And you have these electrons which are being attracted to the nucleus because of this positive charge here and their negative charge. And they're essentially whizzing around far away from the nucleus. It turns out that the thing that determines what element you have is the number of protons in the nucleus. And the thing that determines the properties of the atom, essentially, the properties of the element, are the number of electrons. Usually, in most normal cases, the number of protons is equal to the number of electrons. So the total charge of the entire atom is 0 because the negative charge from the electrons cancels out the positive charge from the protons. So the reason why similar elements seem to be grouped together on the periodic table is that the periodic table arranges the elements based on the number of protons and therefore the number of electrons that these elements have. So the top row has 1 proton, 2 protons. The second row is 3, 4, 5, 6, 7, 8, 9, 10. And then going down, it increases in the number of protons from left to right. And these columns here end up having similar configurations of electrons, which is why this column has similar properties and this column has similar properties, but these properties of these two columns are very different from one another. Really, the periodic table is not this square object. It's essentially a continuous scroll where you go from left to right and then back down left to right again. So instead of reading it like this grid, we should read it like a rotating scroll that goes all the way around and comes around. And every time we just increase the number of protons in our nucleus. And it ends up showing that the similar number of electrons have similar properties. So in addition to the elements, there are some substances that aren't fundamental and that aren't based on one single type of atom, and in fact are based on multiple atoms that are bound together. We call these conglomerations molecules. Here's an example of one. We have two atoms here of hydrogen. Sometimes if they get close enough together and are in the right situations for this to happen, you can form them into a molecule of two hydrogen atoms bound together, more loosely than an atom is bound to itself, but strong enough to hold together in general under normal circumstances like we would see here on Earth in the temperatures and pressures that we have here. This is a different way to get different types of properties from this atom. The properties of an H2 molecule, hydrogen 2 molecule, are different from the properties of atomic hydrogen. The hydrogen atom is just about the simplest molecule that you can think of. There are more complex molecules as well. Here's another one that many people are familiar with. This is the water molecule, where you have a hydrogen atom up here, a hydrogen atom up here, and an oxygen atom down here. All three of these are bound together to create water, which we drink every day to survive. You can get even more complex molecules by adding together many different atoms. This is what we call an organic molecule. It's made up of hydrogens, nitrogens, carbons, etc. And as you keep increasing this complexity, you can get very large and very complex molecules, such as the DNA molecule, which contains the genetic code that tells our cells how to reproduce themselves.